I'm Dr. Mark Simmonds from the Centre for Reviews and Dissemination here in York, and I have been working with, I should obviously acknowledge my various colleagues, Julian Elliott and Joe from Australia, Georgia Salanti in Switzerland, and Adriana Nicoladu and Julian Higgins as well in Bristol, who have been working with me on this research project, where we've been thinking at Cochrane's request about how we might best update meta-analyses, given, as I say, that Cochrane Reviews and meta-analyses are expected to be updated and are obviously, as more and more evidence is produced, they require more updating over time. So just to think about, obviously we have to think about when we might want to update a meta-analysis. Obviously you need to think, because updating is a time-consuming process, you have to go through the whole, the search process, data extraction, quality assessment, meta-analysis, and so on. We don't want to do an update when perhaps we're not going to find anything, or when it's not going to have any meaningful impact on our results. So should we, for example, do a update our meta-analysis, our review, every time a new study is identified, or should we be perhaps more focusing on when studies might alter our conclusions? Other issues that might arise, obviously, is a question of when can we reasonably stop updating a review or a meta-analysis and say that we think we have some kind of conclusive result, either in favour of an intervention or suggesting that an intervention is not worth pursuing. Again, and that might also indicate which meta-analyses and reviews should have priority, because obviously some reviews, for example, might be highlighting that there looks like a benefit of an intervention, but we might not have got a statistically significant result yet, but it's perhaps looking favourable. Whereas other reviews, there might be very limited evidence, no particular impression that anything is going on, or we might not want to prioritise those for reviews. I'm going to focus more on the issues of what our conclusions are from any meta-analysis we do, and how those might change over time. Because obviously, if we sort of jump to the gun perhaps too soon on a meta-analysis and either say perhaps that this intervention is effective or this intervention is ineffective, and a few trials might come up later on which change our minds, we need to be cautious about that kind of drawing conclusions which may well change with time. Obviously, we don't want to mislead people into incorrect conclusions based on limited data. So I'm going to focus on the two sort of classical statistical errors, type 1 error and type 2 error here. Type 1 error, of course, is the problem of assuming that intervention works or is effective when in fact it isn't. And of course, we classically set that at 5% with p-values of 0.05 or 95% confidence intervals. Obviously, however, of course, the problem there is that the classic 5% type 1 error is based on a single analysis, a single outcome, or a single meta-analysis. And so the more, classically, obviously, we're probably familiar with things like one-for-only correction, the more analysis we do, the higher the type 1 error becomes, and we need to correct for that. And the same problem occurs if we're going to update a meta-analysis as well. The more meta-analysis we do, the more updates we do, obviously the more chances we have of getting a false positive, a type 1 error outcome. So the question is, if we just use a sort of conventional meta-analysis, either fixed effect or random effects meta-analysis, for example, in RevMan, can we accept a conventional statistically significant meta-analysis, with a 95% confidence interval that excludes the null in the classical sense, so the diamond is all on one side of the forest plot, for example? Can we accept that as suggesting a genuine benefit, or do we need, given that we're going to update our systematic review, more conclusive evidence than that? So I'm going to think that here is an example of a cumulative meta-analysis. This is a completely artificial example, by the way, and this is a cumulative forest plot rather than a standard forest plot. So in this case, the topmost square and line represents the first trial, then the second one represents the meta-analysis of the first two trials, the third is the meta-analysis of the first three trials, and so on until you get down to the meta-analysis of all the trials at the bottom. And if we sort of follow that through, we can see that by the third trial, we would have what we would consider to be in our meta-analysis a conventionally statistically significant result, with let's assume that the positive is a favourable result. And we conclude, if we had done a meta-analysis after the first three trials, that the treatment works. But obviously we can see that very quickly, even within a couple of trials later, we're we're pretty much back to an effect estimate that lies on the null, pretty close to the null, and a very wide confidence interval that clearly spans 0. So we're no longer in any way convinced that there's a benefit of this treatment. So you can see that if we jumped straight in there on the third treatment and said in our meta-analyses in our Cochrane review and said this looks like a promising treatment, would have been very misleading. But even then, of course, if we carry on, if we could consider we might have done a meta-analysis much later, and you can see if we go right down to this level, we can see in fact there's a statistically significant result in the opposite direction now, in the direction of, in this case, in effect, a harmful result. And if in fact, but ultimately, if we include all of them, what we'd probably conclude ultimately is that this is a non-beneficial, effectively ineffective treatment that essentially is doing nothing at all. So in this rather artificial example, we'd actually have 4 completely different conclusions at 4 different times through our updating process. And so clearly that's kind of the situation we want to avoid. We don't want our conclusions of our Cochrane review to be changing every single time we do them. Obviously, we lose sort of confidence in systematic reviewing and meta-analysis if that was to occur. So obviously type 1 error, as I said, that increases the more analyses we do, so the more updates to our meta-analysis, to our systematic review we do, and so the more studies that go into it. And this just gives, this graph just gives an indication of sort of how quickly that problem will rise. So we hit a sort of a 10% type 1 error after about 5 or 6 or 7 studies or updates, rising rapidly to sort of 20 and even up to 30 meta-analysis once we've hit about 100 studies. So you can see the more studies we have in our meta-analysis, the more concerned we are going to get about a type 1 error, a significant result when there shouldn't be one. So thinking about type 2 error, which is the opposite, of course, that's the idea of assuming an intervention isn't effective when in fact it is. And obviously that's an issue, of course, because that isn't controlled at all in a conventional meta-analysis. We don't have any, a standard forest plot does not give you any indication of type 2 error at all. And so the issue there is obviously if we're getting a meta-analysis which doesn't appear to be showing any benefit, the result looks pretty close to the null, when can we confidently say this is not worth pursuing any further? We can say this treatment simply doesn't work. A little bit harder in many ways. So here again, we take an artificial cumulative meta-analysis here. You can see sort of even after about the first 5 or 6 trials, we're looking at a situation where the meta-analysis doesn't look very promising. You can see the result is quite close to the null with a very wide confidence interval. And as we proceed down, nothing really changes in this case. So we might ask the question, well, when should we have stopped updating? Is this third update where I've marked it as definitely stopped now worth doing? Are we just wasting effort with going through all these trials and going through these updates over time? Of course, bearing in mind that down at the bottom there, if there are enough trials, ultimately any meta-analysis will produce a statistically significant result if we get enough data, enough trials over time. So we have to think about ultimately any meta-analysis will produce a significant result. It's just a question of is that a clinically meaningful result or not, and how long is it going to take us to get there? But again, this is perhaps an example where this treatment effect might not be medically beneficial, and we could really have sort of argued that the trial production process in the meta-analysis should have stopped much earlier. I should just sort of put in a warning here to bear in mind that obviously the effect estimate at each updated meta-analysis, the effect estimate is the correct one. It is the correct and the best estimate of the effect at that time. And similarly, the standard 95% confidence interval is also, in some sense, the best estimate of the confidence interval at that time for that meta-analysis, that update in isolation. The issue here is about the decisions that we make on the basis of those effect estimates and confidence intervals. Decisions like this treatment is effective, this treatment is ineffective. We should definitely update this review. We don't need to update this review. It's the decisions made on the basis of these results that are impacted by the type 1, the type 2 error, and the problems that things will change as we do repetitions. Each individual meta-analysis is still valid in the conventional sense, although we might argue, as I've deliberately put the question mark in there on confidence intervals, about whether a standard 95% confidence interval is too narrow given that we're going to be updating a review, perhaps we should take into account the fact that we will update and say be less confident in our confidence intervals, so to speak. So the obvious question is sort of how do we deal with this? How do we go from a conventional meta-analysis that we'd see in RevMan to something that tries to address the fact that we are updating our reviews and we might need to consider type 1 and type 2 error rates as a consequence of updating? And the main approaches that are used are based on parallels with sequential trial design. And in a sequential clinical trial, the idea is that we randomize patients and we keep performing interim analyses through the trial with an attempt to stop the trial at the point at which we find we've got a conclusive result, either a clear indication that the treatment works or a clear indication that the treatment is ineffective. And the classical sequential trial will set a type 1 error rate, normally 5%, and set a type 2 error rate or the statistical power equivalently, along with some desired clinical effect, like the clinically minimal meaningful effect. And we can sort of convert that idea into a meta-analysis idea by just replacing trials with meta-analyses or reviews and interim analyses with meta-analyses performed through the review. So we consider an updated meta-analysis process or a cumulative process like a sequential trial where we're doing repeated interim analyses throughout the updating process. And so the theory goes that if we can treat a meta-analysis a bit like a sequential trial, we can borrow the methodology from sequential trials to use in meta-analysis. Obviously, that's not a perfect analogy, because obviously we know that a clinical trial is obviously highly controlled. We're controlling the patients who are going into it, we're controlling the times of analysis, and we're controlling the total sample size and so on. But in a meta-analysis, obviously we have no control over when we don't have much control over when the studies are going to come in, so when we're going to get new data, nor do we have any control over the size of those studies, so we don't know how much data is going to come in at each interim analysis. In fact, that's not a huge problem, because most of the methods designed for sequential trial analysis can handle issues like varying amounts of data coming in at different times and inconsistent analysis times. The other big issue, of course, is heterogeneity. We wouldn't expect heterogeneity within a single clinical trial, but obviously we might well expect it across a meta-analysis, because we're dealing not with a single study, but with multiple trials, multiple studies, and they'll have different protocols, and obviously the effects may not be consistent. And that does have a big impact, because, of course, heterogeneity is we have to account for heterogeneity. We're going to thinking about random effects analysis here throughout. So we need to take account somehow of the heterogeneity, and that's a bigger issue, and how we adapt sequential methods to meta-analysis. So along with my group, we did a sort of a review of available methodology for updating meta-analyses over time. I'm not going to go into the details of it here, but we essentially found 4 key methods. There are 2 methods based on sequential trial design that control both type 1 and 2 error. That's, as we'll discuss in a second, sequential meta-analysis and trial sequential analysis. There are 2 slightly simpler methods that control only for classical type 1 error. I will call those the law of the iterated logarithm and what I call the Shuster-Pocock method. And I'm going to look at all of those 4 methods this morning. There are various other options available. You can do, for example, a completely Bayesian meta-analysis. Instead, we're using informative priors, for example. That has been considered as an option. There are various methods, not particularly good methods and rather outdated methods, perhaps, for looking at whether a meta-analysis is robust or stable to the addition of further trials. And also there's been quite a lot of work done on whether or not what the consequences of adding a new study might be, or the gain in statistical power from adding a new study. I'm not going to consider those methods because they're a little bit more ad hoc than the formal sequential methods today, but so I'm going to focus on the first 4. So starting off with sequential meta-analysis, the first of those methods, which was developed by Julian Higgins, me, and Anne Whitehead back in 2010. The idea here is that instead of a conventional meta-analysis, we calculate what we call the cumulative Z-score, so the cumulative effect divided by the standard error, and the cumulative statistical information, which is just 1 over the variance, at each updated meta-analysis. So rather than addressing it in terms of treatment effect and constant, we deal with Z-scores and statistical information. And if we do that, we can create a sort of a boundary in Z and information space where we can say that if we cross a boundary, we believe that we have a conclusive result, either in favor or against the intervention. And that boundary is constructed so as to control the type 1 and type 2 error, so that the cumulative type 1 error over every analysis adds up to 5%. And we're also aware of what the type 2 error is across the full meta-analysis. In this method, we also conceived a way of trying to handle the uncertainties in heterogeneity in dealing with a meta-analysis over time. Because obviously, if we do a meta-analysis and we repeat it, our estimate of heterogeneity is going to change alongside the estimate of the effect changing. And so one particular problem, of course, is what happens if we underestimate heterogeneity early on. Our confidence intervals will be too narrow, and we may reach a statistically significant result when, in fact, if we added a few trials later, we'll find there's actually much more heterogeneity, and we really shouldn't have been that confident. So what we did in this sequential meta-analysis approach is to essentially use a sort of a semi or pseudo-Bayesian analysis, where we set a prior estimate for the heterogeneity, normally set quite high to avoid accidental underestimation of heterogeneity, and then we combine that prior estimate with a Desmonian layered or other estimate based on the trials, and that generates obviously a posterior estimate of heterogeneity, and we use that posterior estimate of heterogeneity to update our analysis. And the idea, of course, there is that we avoid the risk of misestimation of heterogeneity early on, but over time, the real data should sort of crowd out the prior, so that we are trending towards a true heterogeneity in the meta-analysis over time. So just to illustrate all these methods, I'm going to look at an example cumulative meta-analysis. In this case, this is actually an example in peptic ulcers that we used in the original sequential meta-analysis paper. And here you can see I've highlighted that a conventional meta-analysis would have been statistically significant after the fourth update, the fourth trial, but that significance would just have been lost by the seventh trial, marked in red. And again, it would have gone back to statistical significance with a cumulative risk of about 0.5 after the after about the 10th trial, and remained significant and hovering around a cumulative relative risk of about a half after that. So we might say that obviously if we'd done a quick naive analysis and said after the fourth trial this was fine, that probably wouldn't have been reasonable. But perhaps after about the 10th trial, it would be reasonable to say we've got a conclusive result that's not going to change much over time. So sequential meta-analysis, if we plot it out, looks a little bit like this. So in this case, the red dots mark each meta-analysis update after each trial, and the black lines indicate our boundaries. So a boundary going above the horizontal line for Z-score would indicate a benefit. A high Z-score means a high treatment effect. So that's a benefit of the treatment. And crossing the vertical boundary means that essentially we've reached the maximum required sample size or statistical information. So we could stop on the basis that we have enough evidence at that point to reach a conclusion. And in this case, the first dot represents the meta-analysis after 3 trials, because the first we wouldn't want to do meta-analysis just on 2 trials. So in this case, you can see we stay within the boundaries of the 3rd, the 4th, the 5th, the 6th, the 7th, the 8th trial. The 9th trial, you can see we're just about hovering on the boundary up there, just with a Z-score just above 10, but we haven't quite crossed it. And by the next trial, by the 10th trial, we've crossed both boundaries. So at that point, we could sort of conclusively say that we now have enough evidence to stop this updating process. We've found a significant result, and there is enough evidence as well in terms of sample size to stop updating, which agrees with the previous slide. To move on to trial sequential analysis, this is a similar idea based by Jorn Vetterstedt, who I think is online, and others, Christian Good and others in Copenhagen, which takes a sort of a similar approach where it calculates, based on desired type 1 error and type 2 error, it calculates the required sample size for the total meta-analysis, and it applies alpha spending boundaries to that sample size. And similarly, it takes the Z-score and it will stop for show a benefit if the Z-score exceeds that boundary or if we achieve the required sample size. The only difference essentially between this and the previous method is obviously the sample size has to be adjusted for heterogeneity, and so the sample size may change over time. So here's the same meta-analysis again illustrated in terms of trial sequential analysis, and here you can see the boundaries. The alpha spending boundaries are those curved boundaries which tend towards the classical 1.96 boundary once we've hit the desired sample size, which is just under 600 in this case. And you can see in this case, the third, the fourth, and the fifth trial. At the sixth trial, we're just about hitting the boundary. And again, we just about hit the boundary and the maximum sample size at the ninth trial. And again, at the 10th trial, at the 10th trial, we've exceeded the required sample size and we've got a significant result. So again, we could stop. So you can see in this case, this is fairly similar conclusions to sequential meta-analysis. The third, as I said, the next two methods, they don't consider type 2 error, so they have no sample size control. They just control for the type 1 error, for the fact that the more analysis we do, the more chance we have of getting a significant result by accident, by a false positive result. The law of the iterated logarithm by Lan Hu and Joe Capillieri adjusts, essentially all it does is adjusts the Z statistic using the formula illustrated in the slide, which is chosen because that is bounded as the sample size or the number of trials n tends to infinity, and that controls the type 1 error. The lambda parameter depends on the statistic you're using, and there is some uncertainty about what that parameter should be, but they have recommended, for example, for odds ratios, relative risks, the lambda should be set at 2. So the law of the iterated logarithm method essentially just adjusts the Z statistic. And we can see what happens here. So on the vertical axis is, instead of the standard Z score, I've got this penalized Z score from the previous slide, and obviously we're going to wait and see if that exceeds the conventional 1.96 boundary for a 5% type 1 error. And you can see here it takes a lot longer to cross the boundary than either trial sequential analysis or sequential meta-analysis. I'm not going to count those, but I think it's sort of around about the 15th, 16th, 17th trial before the crossing boundary, the stopping boundary is crossed. So it's a rather more conservative in this case. It takes a lot more studies to reach a conclusion. And finally, a method developed by John Shuster in 2013. Rather than using Z-scores, it compares things to a T distribution instead of a conventional Z distribution. And I call it the Shuster-Pocock method because the parameters of that chosen distribution are based on Pocock's sequential boundaries, rather than O'Brien and Fleming alpha spending boundaries, which the other methods use. I'm not going to go into the details of how this works because it's rather too complicated for a single slide, but also the Shuster-Pocock method requires that you specify how many updates you intend to do, which may be a limitation, of course, because we may not know that in advance. And if we do this analysis here, we're comparing the T statistic to some Pocock boundaries, the Pocock boundaries in black. And again, you can see since each red dot is a meta-analysis, this again is quite conservative, taking quite a long time, in this case up to about the 15th, 16th study before a boundary is crossed. So we've got four options here. Sequential meta-analysis, trial sequential analysis, law of iterated logarithm, and the Shuster method. And so what we did in our research project was we essentially took all the Cochrane reviews from 2014 and 2015, which had been updated in those 2 years, which turned out to be, so that's all the reviews in those 2 years that have been updated and included a meta-analysis of 3 or more trials. Since obviously we probably wouldn't want to do this kind of sequential analysis with only two trials. That turned out to be, there are 76 such reviews from 2014 and 2015, and obviously each review has more than one meta-analysis, so that makes for a total of 286 meta-analyses to consider. I should note here that it's not necessarily the case that each of those reviews did the meta-analysis or reported the meta-analysis, but they had the data available such that meta-analysis could be done on the outcomes presented. And of those meta-analyses, they're about 70%, just under 70%, were binary outcomes, and the rest were continuous data outcomes. and about 60% of those produced a conventionally statistically significant result at the 95% confidence interval 5% p-value level. So slightly more significant results than non-significant results. As we'd expect from a Cochrane review, most of those reviews were quite small, only median of 9 trials per meta-analysis, although they did go up to a maximum of 200. And in the heterogeneity, looking at heterogeneity in terms of I-squared, generally speaking, fairly low I-squareds were observed. 32% of all meta-analyses had an I-squared of 0, and only 7% had an I-squared exceeding 90%. So on average, fairly low, little evidence of heterogeneity, low heterogeneity levels. So in this case, I applied to all those meta-analyses a standard conventional cumulative random effects meta-analysis, which I'll refer to as the naive method, so not attempting to adjust for type 1 or type 2 error at all. I applied the trial sequential analysis with the sample size adjusted for heterogeneity, and the sequential meta-analysis with no Bayesian adjustment for heterogeneity, and with a prior equivalent to a 50% I-squared or a 90% I-squared to adjust for heterogeneity. So that's using the Bayesian prior adjustment with an I-squared of 50% or 90%, and then also the law of iterated logarithm and the Shuster-Pocock method. And this, in one side, essentially summarizes what the results of that analysis found. If we focus on the left-hand side, that's the 100 or so meta-analyses which ultimately there was no statistically significant result. So essentially, if we found a significant result anywhere in the update process, we consider that perhaps to be a false positive signal. And you can see, so in this case, green indicates a positive signal, a favorable effect. Red indicates that the meta-analysis doesn't reach any convincing conclusion. There's no statistically significant result at any point. And blue indicates that we would cross the vertical maximum sample size boundary for trial sequential analysis or sequential meta-analysis. So that's a boundary saying we've achieved sufficient sample size that we can stop the updating process. And you can see that if we look at the naive meta-analysis at the top there, we can see that it's about 13–14% of all of these 100 meta-analyses give a significant, at some point in the updating process, produce a statistically significant result, when ultimately there isn't, when you look at all the trials together, there is no significant result. So that's a concern, because clearly that's higher than the classical 5%, that's higher than we'd like it to be. So there's 13% of these analyses are producing what appears to be a favorable result, when in fact there is no treatment benefit. You can see that all the other methods essentially have 0 or very close to 0 type 1 error. They never produce, apart from law of iterated logarithm right at the bottom there, they never produce a false positive result at any point. So they are all doing what they should do, and they are all controlling for type 1 error properly. You can see also how little of that, how very few trials end up in the blue category, in the category of reaching the required sample size or information. And that's sort of parallel to what people like Rebecca Turner have shown before, in that most meta-analyses in Cochrane are underpowered to detect an effect. So they simply don't, the sample size isn't big enough to detect the actual observed effect that was seen in the meta-analysis. So again, that's an issue with even meta-analyses are not big enough to detect the effect that's actually in the real effect. If we look at the right-hand side of the plot, these are the meta-analyses which do produce, when you look at all the trials, a significant, statistically significant result. So in the case of naive meta-analysis, of course, that's pretty much all of them by definition. And you can see that we're seeing that all the other methods have fewer cases where the meta-analysis will stop or cross a boundary. So, for example, trial sequential analysis, only about 60% or so would actually find in favor of the treatment intervention, and similarly for sequential meta-analysis, about 60–70% would find in favor of the treatment effect. And so we consider that, obviously, because here we don't know, in this case, because these are real analyses, what the true effect is in any of these cases. That could either be because the new methods are underpowered. They simply, because they're conservative, they take longer to stop, so there are going to be cases where there's a genuine effect when they don't detect it, Or it may be that we've got a load of meta-analyses in Cochrane which perhaps we're overconfident in the results, that we perhaps shouldn't be confident that the result is statistically significant. Perhaps genuinely, for example, there are, for example, taking sequential meta-analysis, are about 25% of meta-analyses where, in fact, it looks statistically significant in a naive analysis, but perhaps we shouldn't be convinced of that result. But considering sort of the issue, obviously we'd expect these methods to take longer to reach a conclusion because we're being more cautious, more conservative. In fact, most of the time they don't take much longer to stop. This plot shows for each method how many trials are required to reach a positive conclusion, more than a conventional naive meta-analysis. And you can see that the most common result for sequential meta-analysis, for trial sequential analysis, for iterated logarithm is 0, the highest bar there is actually at 0. So most of the time, these methods will cross a boundary at the same time as a naive meta-analysis would have reached a significant result for the first time, or at worst 1 or 2 trials later, as you can see. The exception here is the Shuster method in the top middle tends to take several trials more, I think on average about 3-4 trials more before it will reach a conclusion. And similarly, if we put the very strong prior heterogeneity prior in the sequential meta-analysis approach, that 90% I-squared, so we're very conservative about what the heterogeneity might be, that again will increase the number of trials before we reach a conclusion. So generally speaking, these methods aren't delaying genuinely positive results by very much, perhaps by 1 or 2 trials. So in a real Cochrane review where we're not going to update every single, we might not update every single trial, we're probably not delaying updates. They're delaying finding a positive conclusion very long. I should note here that that analysis has been done on the basis assuming that we had done an update every single trial, which of course is not realistic. We're not going to be updating most Cochrane reviews after every new trial has emerged. We don't have the time to do that many updates. So as a sort of approximation to a more realistic approach, I'm going to assume that obviously we're not going to do our first meta-analysis until we've got a reasonable number of trials that we think it's worth doing a meta-analysis. And I'll take that as 50%, half of the available trials. And then we're going to do an update after 70% of the trials are available, 90% of the trials are available, and all of the trials are available. So we're going to do an initial meta-analysis with half of the trials, and then 3 updates as we go further through. So that's intended to sort of vaguely more realistically represent a Cochrane updating process that will update occasionally. We'll probably only do 2 or 3 updates, and we'll have a fairly large amount of data before we even do the first meta-analysis. In fact, looking at the results of that, so here looking at sort of the equivalent plot from 2 slides ago, it doesn't actually make a great deal of difference to conclusions. We're still seeing an elevated sort of type 1 error from naive meta-analysis. It's slightly reduced, it's dropped down to about 11–12% here, but not really changing very much. And otherwise, the conclusions for the other methods are largely unchanged. So things doing a meta-analysis after every single trial and doing a sort of occasional update doesn't actually have much impact on our conclusions about how these methods work. It doesn't make them any worse or particularly any better. Although we might argue that now, you know, if a naive meta-analysis, the type 1 error has risen to about, is it 12–11% rather than the 5% it should be, is that perhaps an increase, an inflation of type 1 error we can live with, or we are willing to live with an increase of up to 10% when it should be 5%, and that's perhaps something we can discuss at the end. So more formally, to sort of complement this analysis of real Cochrane reviews, we also did a simulation study so that we can actually control what the genuine effects are. So in the simulation study, we used 2 treatment effects, either a null treatment effect, so to look at false positives, or a genuine treatment effect of 0.1, varied the number of studies in the meta-analysis from 5 to 50, so to represent sort of typical ranges in Cochrane, and again, varied the heterogeneity from nothing to 90% I-squared. In each case, the meta-analysis had 9,000 participants. Every single meta-analysis had 9,000 participants chosen because that would have 90% power to detect that 0.1 effect size with an I-squared of 50%. So that sample size, most meta-analyses should detect that effect if it's there with a 9,000 sample size. So focusing first on the false positives, the type 1 errors, so this is the case where there's no genuine treatment effect. Here I've given the example where we had 20 trials in a meta-analysis, or 20 equivalently 20 updates, with an I-squared of 25%. And you can see that naive meta-analysis has quite a big problem here, that the type 1 error is up at 25%, which I think should concern anybody. Most of the other methods, sequential methods, sequential meta-analysis, the Shuster method, or the Iterated Logarithm, do effectively keep the type 1 error at or below 5%. Trial sequential analysis just creeps up in this example. I think it's a slightly odd example here, creeping up to 9%, but I think that's more of an odd one out. As you see, if we compare that, this shows the complete data. So we've got the number of trials going from 5 up to 50 along the top, and in each individual subplot, and the I-squared is going from 0 to 90%, going down the plot in each subplot. So if you sort of look horizontally across, you can see as the number of trials increases, particularly for naive meta-analysis, the false positive rate does inflate quite rapidly. Even with no heterogeneity, we're going up from about 6-7% with 5 updates or trials, right up to sort of 25% when we've got 50 trials in a meta-analysis. And similarly, as we go down, you can see that heterogeneity also has a detrimental effect in conventional meta-analysis. The more heterogeneity is, the more rapidly type 1 error inflates. And you can see in the most extreme cases, with 50 trials, and at the bottom right, 50 trials and I-squared of 90%, we're hitting type 1 error rates of 45% for a conventional meta-analysis, which is obviously completely unacceptable. And again, looking at the rest of the plot, we can see that most of the methods generally contain type 1 error to be around 5%, though things do get slightly problematic as the heterogeneity increases. If you've got very few studies and high heterogeneity, it's difficult to estimate that heterogeneity, and so we've got more risk of underestimating the heterogeneity. And I think that's probably an unavoidable problem. There's very little we can do in some senses if we have high heterogeneity and few studies to estimate it. But you can see that as the number of studies increases, so we're better able to estimate heterogeneity. Looking, for example, at the very bottom row with I-squared is 90%, you can see the type 1 error does drop back for trial sequential analysis, and for sequential meta-analysis down to around about 5% or less as the number of studies increase. The other issue, of course, is the type 2 error, or I'll think of that in terms of the power here to detect an effect. So this is the case where we have a genuine treatment effect of 0.1, and again, I'm going to look at the case where we've got 20 trials in a meta-analysis and an I-squared of 25%. And so each of these colored lines show the percentage of meta-analyses that have reached a conclusion by the given trial. So that's sort of a representative of the power over time, over trials for each methodology. And you can see that the lines in the middle are sort of the purpley one, which is trial sequential analysis, the orangey one, and the yellow one, which is sequential meta-analysis. They do, by and large, they increase to the expected 90% rate, which is the dotted red line there. So they are doing what we expect. They are trending towards 90% power, which is what the simulation study was designed to have as we get to the maximum number of trials. Obviously, a naive meta-analysis has a higher power, but that's driven largely by its inflated type 1 error. You can see, though, that an issue that comes here, the law of the iterated logarithm in red has very poor power properties for reasons I still have to admit I can't quite work out. It's showing very poor performance in terms of power. It's not achieving 90%. And the dark blue line, which is the sequential meta-analysis with very conservative heterogeneity prior applied to it, you can see that although it does achieve 90% power, ultimately it's very slow in getting there. So we're being perhaps over conservative by putting such a high prior estimate of heterogeneity into our sequential meta-analysis approach. It's a bit difficult to see the results on this slide, but again, this is the results of all the analyses ranging from 5 trials to 50 trials on the horizontal and I-squared of 0 to 90% on the vertical. Just to note here, generally speaking, in all cases, the trend for sequential meta-analysis in orange and trial sequential analysis in purple does trend towards 90% as we expect. It's perhaps a little difficult to see, but the Shuster method unusually does trend towards 90% when the number of trials is large on the right-hand side, for example, 20 trials or 50 trials, but doesn't do quite so well when there are a few trials. So Shuster seems to have some problems when there are very few trials in the meta-analysis, again, for reasons that are unclear. So just to sum up those methods, a conventional meta-analysis, as we might do in RevMan, clearly, certainly from the simulation study and from the practical application to Cochrane Reviews, there are simply too many inappropriate positive conclusions, and we have to be aware that if we're just going to use a standard RevMan style approach in an updated meta-analysis, they do have an elevated risk of producing significant results when they genuinely shouldn't be there. So we are going to have to be cautious going forward about that, I think. But perhaps, as is shown, the elevation is only in realistic most reviews. It's only going to go up to about 10, 11%. So perhaps that's, we can argue, can we tolerate that increase? As long as we're aware of it, can we tolerate that without having to go to more complicated methods? I haven't shown it here, but there's also evidence that the effect estimates are biased. If there is a significant result, unsurprisingly, it's probably because there's an overestimate of that result. So significant results in conventional meta-analysis tend to be overestimates of the truth. And also, we talked about perhaps we've got about 25% now of analyses in Cochrane that are showing significant results, when if we do a sequential method, we wouldn't have crossed the boundary and we wouldn't be convinced. So there perhaps quite a large pool of meta-analyses in Cochrane, which perhaps are not as convincing as we think they are. Trial sequential analysis does control for those errors, but we have to do things like choose a desired treatment effect, which may be difficult. We'll have to choose a further clinically meaningful effect, which we might need specialist advice for. They are more tricky to run. You need specialist code or software to do it. And the tricky problem I've found with this method is that the sample size, if you're at cancer heterogeneity, the sample size varies with time, which can lead to some inconsistencies in what you conclude over time. I tend to find that switching to using statistical information, rather like sequential meta-analysis, can solve that problem, but I don't have the time to discuss that in detail here. Similarly, sequential meta-analysis, again, it's tricky to run, although it does manage to control for those errors. It has the problem that you have to deal with statistical information, which is a bit more difficult and unintuitive to deal with. And the boundary, we're quite constrained in those boundaries that we use to decide whether we've got a significant result or not. And certainly my results suggest that the Bayesian adjustment for heterogeneity that we proposed in the original paper is perhaps rather conservative in practice and maybe isn't really needed. We can do it without that cunning adjustment for heterogeneity. The iterated logarithm controls only for the type 1 error, but it is quite simple to use. But there's quite a lot of evidence of biased treatment effects, and it's simply too conservative, I think. The power is very low. And also there's issues about which lambda parameter is the most appropriate one to use. And similarly for Shuster-Pocock, this, again, it's very easy, it's fairly simple to implement, but it seems to only be a useful method when there's quite a lot of trials in the meta-analysis, so 20 plus, which of course in Cochrane is not a very common event. And there's still there's an issue about how many, you have to pre-specify the number of updates, of course, which you may not know in advance, and that can have an impact on the findings. So all the methods have some benefits and some demerits to them, which need consideration. So I think I've lost the title here, but I got to think, so to sum up, although we are concerned about just using conventional naive meta-analysis, perhaps that problem for most Cochrane reviews that are only going to be updated occasionally, and of course lots of Cochrane reviews never do get updated, perhaps it's not such a big problem. As long as we're aware of the issue, perhaps we don't need to go to these more complicated methods. We can argue perhaps the more complicated methods will delay a statistically significant result. They will delay a positive finding by a few trials, perhaps. So are we willing to accept that slight delay in reaching a firm conclusion? Another issue, of course, is what is the real aim in a Cochrane review? Is it are we looking at decision making trying to decide whether treatment works or not, or are we just trying to present the evidence and give an estimate? If we're looking at the latter, perhaps these methods aren't so required. And this is just, of course, adding complexity that we don't really need. And if we are going to use them, obviously we need to think about when we might implement them. So obviously, ideally, they should be in a protocol. We should be protocol specifying that we are going to use these kind of methods. But we might argue, do we need to use them at the first analysis? Do we start implementing them at the first update? Or are they really only required if a conventional statistically significant result is found? Because it's really avoiding type 1 errors that these methods are beneficial for. So do we need to implement them until we've actually got a potential type 1 error? Or similarly, perhaps they're more important when we've got very limited evidence. So we're concerned that, a significant result based on a very small sample size might be misleading. And so to sum up, I think a lot of this issue raised up whether we use these methods is getting back to what Cochrane reviews are really for. People have argued that we don't need these methods because a Cochrane review is purely presenting the best evidence. And if all we want to do is present here is the best estimate of effect at this current time, then arguably perhaps we don't need these methods. I mean, or are we using Cochrane reviews to make decisions, either about whether a treatment should be used or to guide and influence future trials in the area? And personally, I think that we cannot avoid the fact that Cochrane reviews have to be used for decision making somehow. People are going to go away and use them to make decisions, either about treatment or trials, and we shouldn't sort of pass the buck, as it were, on this in pretending that we're only interested in best evidence, best estimation, and so these kind of issues, sequential methods don't apply. So I think we certainly need to be concerned about the issues about whether in an updating process, particularly if we move to much faster, rapid updating processes, about whether we are giving reasonable conclusions by using conventional meta-analysis, and do we need in those circumstances to switch to sequential methods? And I will stop there and take questions. Thank you very much.